Hi everyone, I'm Harshit from Infineon.
Hi everyone, I'm Janish from Infineon.
In this video, we'll introduce you to Infineon's high-performance AI SoC power supply solutions. This is based on Infineon's OPTIREG family of multiphase power delivery solutions for automotive, robotics, and more. In this video, we'll be demonstrating Infineon's smart power stage product using TLF12505A multiphase automotive evaluation kit. This is the evaluation board for the TLF12505A power stage. The evaluation board setup consists of motherboard with Infineon's power stage, digital controller daughter card, onboard load emulating the SoC behavior, and liquid cooling system. This setup allows us to evaluate dynamic load transient response. The board provides 4 voltage outputs to power SoC core rails, also known as 4 loops. This load port setup can emulate transient load profiles of each loop that can be individually configured via GUI provided. The load board supports DC currents up to 1200 amps at a very low voltage ranging from 0.4 to 1.8 volts, with bandwidth extending up to 1 MHz. We can also reach up to 2000 amps peak current with liquid cooling while achieving extremely fast transient slew rates of about 4800 amps per microsecond. The system uses 8 configurable 150 amp load cells, and it also allows us to run 2 independent transient loops simultaneously for advanced dynamic testing. Here's a specifications example where the DC-DC converter is operating at a switching frequency of 650 kHz, and we are using 85 nH inductor per phase of the multiphase buck converter. To meet system requirements, the allowable output voltage undershoot is limited to 150 mV and the overshoot is capped at 200 mV.
Let's look at the setup. First, connect load balancer with cooling system mounted on the top of the power board with the help of 8 to 6 pin connector. The load board and the control board are interfaced using USB Type-C cable. Oscilloscope and function generator are connected to the PC. In this setup, function generator generates PWM pulses to the control board through the coaxial connection. On the power board, we measure current monitoring signals for 3 phases. J47 measures output voltage at sense P. Output current measurement is taken from the control board. All the signals are measured differentially using differential probes. This is the bouncer GLS GUI using for transient testing. Here we configure the key parameters such as gain, currents, slew rates, duty cycle, and load frequency. Once these parameters are entered according to the test requirements, we simply start the 3D test to initiate transient operations at the set conditions. The oscilloscope capture shows the transient response of the power board during load step generated by the bouncer. The yellow trace represents the phase current switching between low and high levels with an average I1 voltage of 700 mV, which translates to 140 amps per phase. The blue chair captures the output voltage response where we can observe the voltage drop and recovery during the rising transient as well as overshoot during the falling edge. The orange trace represents the output current measured at 1050 mV, which translates to 420 amps. This 3D surface plot shows how the output voltage overshoot and undershoot vary with transient parameters such as load frequency and duty cycle. On the left, we can see the maximum voltage response with the peak overshoot reaching about 0.997 volts. On the right, the maximum voltage response is shown, while the worst case undershoot drops to approximately 0.651 volts. From these plots, we can tell that both overshoot and undershoot margins are well within the allowable specification limits.
So that's a quick look at our automotive multiphase power supply solutions and few evaluation tools for low transient tests. To learn more about the product, please visit our website. Thanks for watching.